Jai Hind. I am Professor Devendra Singh in Mechanical Engineering Department at AKGEC Engineering College. This is our second lecture under this topic, Design Against Fluctuating Load. And in the last lecture, we have covered about various types of the fluctuating stresses. We have understood what is the meaning of the amplitude stress, the mean stress. We have discussed about the fatigue and fatigue failure. Uh, and in the last lecture, it was clear that fatigue failure is more dangerous as compared to a static failure, because in a static failure we get some indication, some warning before failure. But in case of the fatigue failure, there is no indication, no warning. That's why this is more dangerous. And uh, as far as the definition is concerned, we have discussed about the definition that it say that the fatigue failure, if the material is subjected to completely reversible stresses, then and more than 90% cases it is observed. It has been observed that it fails below the yield point. So this is very dangerous from that point of it. That point of view. That point of view also. That point of view also, because as per the definition, before yielding, before any considerable deformation, fracture in 2 points. Fatigue failure is a physical fracture. So we have come to the point where we should understand how is it possible that it fails below the yield point. So mechanism of fatigue failure we were discussing in the last lecture. So the fatigue failure uh, mechanism it took place in two steps. First is the initiation of crack. Initiation of crack, and further this propagation of the same crack. This crack, initial crack or initiation of crack, may be a hair-like scratch on the surface due to the machining. It may be the crack inside due to the lattice defect or the material imperfections that may be possible. Composition may cause this variation of the strength. That may be a reason. And as the crack is propagated due to the completely reversible stresses, now if we consider the stress F upon A, so and the last courses of strength of material engineering, mechanics and material science, we have understood we are always interested to have the maximum magnitude of stress or maximum load which will come into the picture during the application, that is to be bared by the element. If the designed element or design member will be able to bear this maximum force, then design is good. So as far as the engineers are concerned, they are always interested to have the effect of maximum magnitude of forces. So this is sigma is equals to F upon A. So as this crack propagate, this area will get decreases, and the magnitude of force F will remain same, F max. Or in case of the completely reversible stress, we are interested to have the amplitude force Fa, and this Fa is divided by this area. If area is get decreases continuously, then this stress level increases continuously. So it is true that no material can fail below the yield point. However, it is observed loading is not up to the yield point in the uniaxial uh, tensile testing at UTM, and it fractured into pieces. So, in fact, what happens due to this reduction, which I am not able to observe if it is not external effect on the surface of external effect on the member, if it is internal, then the area will be reducing continuously. It is increasing, stress is increasing, induction of stress, magnitude of stress increasing, and at certain point this induced stress will reach to the point where this becomes above the strength of the material, and it will fail, it will fracture in two pieces without any warning, and this is called the fatigue failure. So, I think it is clear what is the mechanism of fatigue failure and how is it how it has failed below the yield point and more than 90% cases. So, in fact, it is due to this propagation of crack, and this crack propagation, the material which is available to hold the resistance will become continuously reduces, and the area get reduced, and in fact I have made it very clear. So, to design the elements which are subjected to the fluctuating types of the loads, it is very important to understand can we use the same strengths, same material properties which we have used in the design of the members subjected to static load? Definitely not. We have to select another material property to design the elements under this kind of the loading. So, that strength is endurance limit. Endurance limit and another fatigue strength, right? So, what is endurance limit? Endurance limit is the maximum magnitude of completely reversible stress. In fact, it will be the amplitude stress and in case of the complete reversible stress that can be applied on the member for its survival for more than 10 to power 7 cycles of reversal. If any element or any member survives for more than 10 to power 7 cycles of the stress reversals, then it is called the infinite life. It is called infinite life. If it fails below or if it fails earlier than 10 to power 7 cycles, then it is considered as the finite life. So, endurance limit, if we consider the endurance limit to design the member against this fluctuating load or completely reversible stresses, then it is infinite life design, and the fatigue strength This is the magnitude, of completely reversible stresses. It is the magnitude of amplitude stress, I should write here, that can apply on a member for the survival or survival for less than 10 to power 7 cycles or reversals of the stress. It can be anything. So that is called the fatigue strength. So from these two definitions, it should be very clear. A material will have only one endurance limit. Right. This is one point. A material can have only one value of the endurance limit. One endurance limit or its value. And second, a material can have numbers of fatigue strengths corresponding to finite life. Corresponding to finite life. Finite life means the survival for less than 10 to power 7 cycles may be 10 to power 3, 10 to power 4, 6,000, 7,000, 8,000, etc., etc. Now the problem is, how will you define the endurance limit and how will you define the fatigue strength? This is the problem. So we will try to understand how we will decide the endurance limit and fatigue strength of material. For that purpose, we need to draw the SN diagram or SN curve. Now we will discuss the SN curve. R.R. Murray has performed a banding test on high speed banding testing machine on a specific specimen of 85 millimeter of length. This is or we should take this is R250, right, and this is phi 7.5 and this length is 85 mm. All dimensions are in mm. This is, and the surface finish is in longitudinal direction mirror polished. When we will discuss about the factors to modify the endurance limit, then we will discuss about why it is essential to make this specimen with mirror polished surface and longitudinal direction. This is to avoid the stress concentration effects. Then the size effect, this is R250 radius, curvature, etc. And then this will be rotated with high speed machine, and it is subjected to a transverse load W. This load will be changed and the RPMs or reversals will be counted at which it failed or it get fractured, and then we will plot a curve between the load at which it get fractured and corresponding number of stress cycles it has been completed, and the curve obtained is called the SN curve. Another important point about the SN curve, it is plotted on log curve. If we plot it on the normal graph paper, then it was not giving a knee point. That knee point is required to get the value of the endurance limit. It will be clear when we see the ascent diagram. So, first on ordinate axis, here this will be log 10 SF, fatigue strength, fluctuating load, completely reversible. If a shaft is rotated, this is simply supported beam. For example, we apply transverse load, the upper fiber is subjected to compression, lower fiber is subjected to tension, and if this is circular in cross section, then the distance of the extreme fiber for this will have this will be at a radial distance, and the centroidal axis will become the neutral axis. So, the upper fiber where you have applied the load, transverse load, will be subjected to some magnitude of the compressive stress and the same magnitude of the tensile stress on the other side. After 180-degree rotation, the same fiber which was in tension earlier before 180-degree rotation, it will subjected to the same magnitude of the compression, and the fiber which was subjected to the compression will be subjected to the same magnitude of tensile. So, this is a very good example of the completely reversible loading condition. So, the same happen here. So, if W is equals to SUT or more than SUT, if it is SUT, then 0 cycles it complete. This is n number of reversals, base 10, this is base 10, this is log SUT, base 10. Here it get fails. Now, slightly we will get reduce this W. We will reduce the magnitude of this transverse load first SUT. For example, if SUT is 900 Newton per mm square, then the next it will be 980, 970, 960, 50 and so on. And corresponding to each load, we will observe the number of rotation, number of reversals of the stress has been completed, and if we plot, we will get number of points, right? These are the failure points, right? So if we join these points, a straight line on log curve will appear. This is, and after a certain time, in fact, if you see, it will be somewhere at power 10 to power 3. So I will write this is only 3 on log curve. So I will write it is 3. This is 3 means it is 10 to power 3 cycles has been completed and get fractured here. This is failure line effect, and it has been observed that this point is nothing but it is 90% of SUT of the material. Then we move further, the nature will change little bit. These points will be like this, and if we join these points, these are the failure points corresponding to the load W. This is like this. This is like this. At this point lies between 10 to power 6 to 10 to power 7, between 6 and 7. For numerical purpose, for the safe design, we will consider this is around 6. This point we have reached here. Here, this will become straight. Now the failure points become parallel to the abscissa. This will become like this. Failure points. Now it is not going down. So this is the SN curve. This is the knee point. This is the knee point about which I was talking about in last few in last slide. If the loading is below this, then the failure we are not observing, and it will survive for more than 10 to power 7 cycles, then it is considered infinite life problem or infinite life design. All the material is said to be survive for the infinite life, and corresponding to this knee point on the strength axis, this is nothing but this is S prime E. This S prime E is the endurance limit. This is endurance limit, and we will mark prime later. This is called endurance limit. So we will get a single value for this these experiments, but if we apply the loads and observe, for example here 10 to power 4 cycles, these are the failure points, we will get some value. This is log 10 SF. If you apply some other load, you will get, this is suppose 5. Now if load increases, you get this is 4, and corresponding to this failure. So it means this is a strength, this is a strength corresponding to this number of reversals or this life. It means a material can have number of fatigue strengths, but the endurance limit will be only 1. It is clear from here. Now, this is low cycle fatigue. This portion is considered as low cycle fatigue. Only survival for 10 to power 3. Then beyond this, this is called high cycle fatigue. High cycle fatigue. And if the design up to this portion is called finite life design. If our design is 4 up to the 10 to power 6 cycles, the finite life design. And beyond this is called infinite life design. So from here, it is very clear that their finite life design will be based on the fatigue strength, and infinite life design is based on the endurance limit. Another point we can observe from here, we have broken the specimen here, 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 all number of points. These are the arbitrary points I have shown. There may be 100, maybe 1000. So these number of specimens we have broken. So this is an expensive, time consuming process to determine the endurance limit. So we have to think about the way we can find the endurance limit of material, because whenever we will change the material, we need to find out the endurance limit for that material. So we must have some way to determine the endurance limit from a single simple tensile test at UTM. So today this we have discussed about SN curve. In the next lecture, we are going to we will discuss about the way to determine the endurance limit from the material properties of the materials available in our data based on the UTM test. Thank you very much.